Okay, I start. So, Mammatus Clouds, the word comes from the Latin for breasts, which mamma is Latin for breast. You'll see why. Why won't it shift? Sorry. Which way is right? Is forward. Doesn't work. Okay. Okay, so those are Mammatus Clouds. They typically form on the underside of Cumulonimbus Anvils. They can also be found in volcanic ash clouds and sometimes even in jet contrails, apparently, which I haven't seen a picture of, but the paper says. I'll show you what paper I mean. Okay, so some kind of layer of cloud in the atmosphere, underneath which these blob-like things form, and they're Mammatus Clouds. If you've been paying attention, earlier last year, 2017, second half of 2017, a new kind of cloud was a new branch of the the classification of clouds was created. It's called Asperitas. It also looks like a Mammatus, except it's more sheared. Asperitas is Latin for severity, so it's Mammatus cloud under severity. Okay, so I have to point it there. Okay, so this is my cartoon for how a Mammatus cloud forms. You have a deep updraft of some kind, a cumulonimbus usually. It hits it reaches its equilibrium height in the atmosphere, and then it spreads out. And underneath the spreading out thing, you find these blobs. These are the things of interest to us. What we will do is we look at only that part of the problem. We'll assume ideal conditions and so on. I'll explain those in more detail. Yeah. Okay. So most of the pictures and so on I'm going to show you are from this excellent paper from 10 years ago by a whole list of people, including some from NCAR Boulder. So clearly, just from the title, you know that this is a problem which people have been interested in for a long time, and a problem which doesn't have ready solutions. Okay. Very good. So a primer for you. These things are found at a few kilometers in height from the ground. The blobs are a few hundred meters in width, like that. The velocities in the blob are a few meters per second. And once they form, the lobe-like structures, once they form, they last for about 10 minutes. Okay, and if you'll be lucky, if you're lucky, you can get a picture of it. Most interestingly, in spite of clouds and usually how turbulent they are, the underside of these, the lobes themselves are smooth, and presumably the flow around them is laminar. Okay, that's important. Typically found under cumulonimbus anvils, as I was telling you. Also, sorry, Shamruddhi, I didn't wait. Also, they can be found under volcanic ash clouds and jet contrails. Yeah, no, it's working, finally. Okay, so since people have been looking at this problem for a long time, several possible mechanisms have been attributed to how these things can be created. One thing is recirculation associated with the convection itself. So if you have an updraft, deep updraft of that kind, somewhere it has to come down, and that coming down causes a density imbalance, and that causes the thing to over-topple. Other possible mechanisms, radiation is a possibility. Gravity waves are a possibility. Kelvin Helmholtz is a possibility, especially since it does look like, you find these things ordered in rows and columns. So some kind of instability you can imagine may be responsible. Okay, Rayleigh-Taylor may be responsible. One thing that we want to look at, but we have in this talk I won't tell you anything about, is detrainment, which is you have this layer of cloud under which is dry air, no water vapor, nothing. So the thermodynamics of water vapor are highly nonlinear. So the amount of vapor that can exist in equilibrium at a given temperature, it follows an exponential law. So you can have two unsaturated parcels mix and suddenly become saturated. So that leads to cloud air mixing with dry air becoming denser than either the cloud air or the dry air, if that makes sense to you. So that kind of thing is driven by shear. So if you have shear at the interface between the cloudy layer and the dry layer, that can lead to this, that might lead to this kind of mammatus formation. But I won't tell you anything about it because we haven't yet done it. The thing I will tell you about is the mechanism is the settling driven instability. What that is the following. You have water droplets in your cloudy layer, maybe also ice particles, usually also ice particles, and these things fall off because they're finite sized and under gravity they fall. As they fall out of the cloud and into the dry air, they start evaporating. Evaporation leads to cooling. So you have suddenly under your cloudy layer, you have a layer of colder air, denser air, and that density imbalance sort of topples the whole thing. So that's basically the mechanism. If you remember that, you'll understand everything else I'm going to tell you. This much is known. What we're going to do is study study when this will happen, when this won't happen, how strong the effect will be. Okay. Okay. So this is the detrainment thing that I was telling you about. There's a strong shear that way, and you can see the mammatus things forming under them. I should also mention Bob Breidenthal's paper on mixing-driven instabilities of this kind. So they had a tank of one kind of fluid at the top, one kind of fluid at the bottom, except when these two fluids mix, they become denser. There's some reaction there. And they have a splitter plate which they drag out, and the resulting mixing layer, as it grows, it creates a density layer, and that causes the instability. But again, I shan't be talking about that. So this is the one I want to tell you about. So again, I go back to my cartoon. I take that red box there and I model it as cloudy air on top of dry air. The cloudy air contains water droplets. It contains saturated vapor. And for our purposes, the horizontal things are periodic. The vertical things are convective. So a structure that forms and goes out one side, horizontally one side will come back the other, but the structure, a flow structure that goes in or out of the top or the bottom will just keep going. Okay. The inspiration for this was work done by Eckhart and Peter Burns, which Eckhart talked about a couple of days ago. So river efflux into the ocean, and the river carries silt, the ocean has salt. So even though the silty river water is nominally lighter than the ocean water, the fact that the silt settles will cause an instability. So that and that. So you can see the finger-like things. And it was this picture that told us or told me that the mechanisms might be similar. And then we went and actually found that other people have suggested the same thing. Okay, so again, this is again from Eckhart's talk. The settling silt forms a nose region there, and that's the cause for the instability. Okay, so here's my problem in all its gory detail. The cloud fluid has saturated vapor droplets, and we assume that they're both at the same temperature, which may or may not be the case, but just for an idealized case, we assume that they're both at the same temperature. And it has a whole list of parameters, which we will find useful to separate into 2 or 3 groups. This list of thermodynamic parameters are all functions of the temperature. So if you fix the temperature, they're all fixed, which we will do. We will fix the temperature at some reasonable value, and we'll assume that these are all given to us. The other parameters are Reynolds and fluid, of course, and the Prandtl numbers of the 3 scalars: the temperature, the vapor, the liquid, the Prandtl numbers. There's a latent heat term. There's a latent heat term, which is how much hotter or colder will your parcel become if unit amount of water evaporates or water vapor condenses. There's another parameter there, which is the thing that goes into the exponential in the law that governs saturated conditions. But most importantly, there is the number of water droplets per unit volume in your cloudy air, the size of those water droplets, and those two give these other three parameters which we'll be interested in. Tau s is a time for phase change. So if you have slightly supersaturated vapor, how fast will it come to equilibrium? That's the tau s gives you the scale of that. It happens exponentially. Tau s is the time scale for that. Vp is how fast are your particles settling, and RL is the mixing ratio, which is like a density of water vapor or of liquid water in your cloudy air. And these are the initial conditions. There's no flow anywhere initially. All the water vapor and all the liquid water are in the top half. The bottom half is completely dry. Yeah, that's the initial condition. So you can say in the top half, up to a height delta y, there is water vapor and liquid water. After that, it's again dry air. If that picture, where is it? Yeah, if this picture makes sense to you, so from there to there is delta y. Okay, so that's it's called the Clausius-Clapeyron law. It's a law governing saturation vapor pressure at a given temperature. And to simplify life, we will assume that there is no background stratification, so the temperature doesn't change with height in the background, even though in the atmosphere it would. So it's all at one temperature. Yeah, I've told you everything else here. So these are the, in full, these are the equations we're solving. The particles settle, but otherwise they follow the fluid. Otherwise they follow the velocity of the fluid, except that they have a settling velocity. Okay, so first let's try and do linear stability, since you can't work for Raman and not do linear stability. So we linearize the equations. Including the thermodynamics, you linearize the equations and see what comes out. Except we couldn't get this to go anywhere, because the assumption in linear stability is always there is a base state which you can perturb, and the perturbations grow or not based on whether you're in the correct wave number range. Unfortunately, that doesn't work here, because the problem is inherently nonlinear. The base change, the rate at which the base state changes, is the same scale at which the instabilities grow or not. So there's no way you're going to do linear stability. So we have to settle for the next best thing, which is try and solve the equations or a modified set of equations in one dimension and get a net density profile. If you see what I mean, the water droplets settle, evaporate, and you get like an averaged density profile in the vertical. And then you do your stability on that. So we've done that quite recently, in fact. So that's, never mind, I'll come back to this. Where did it go? Okay, so since we fixed the temperature and all other related constants, these four are the governing parameters for us, at least in this one-dimensional study. So you have the mixing ratio of water, how much water is in the upper half, the height of the upper half, and the phase change timescale and the settling velocity. We want to study these things study the problem in terms of these four parameters. Okay? So the best you can do, and I tried everything I know to see if I can pull out a law so what are we interested in? We're interested in this kind of, so the density profile that forms like this. So as the water droplets settle, they form a density profile. We're interested in this density profile. In particular, what is that magnitude and how high is the density profile? Okay, so we're interested in that. And unfortunately, no matter what I tried, I could not get like a reasonable power law out of the 1D evolution equations. I could not, for example, I can't tell you what power this is. This depends as on the given parameters. It does descend. I just can't tell you what power, if there is a neat power law, I haven't found it yet. the one thing I can tell you is if instead of making all these completely independent, you constrain them to be physical, which is you know that water droplets have a certain size. Let's call the size A naught. Vp is proportional to A naught squared, and RL is proportional to it must have been here somewhere. Yeah, so Vp is proportional to A naught squared. It's just the Stokes drag law. So the settling velocity is proportional to the square of the radius of the particle, and the total amount of water vapor, liquid water droplets is proportional to the number density times the volume of each droplet. So if you constrain this to be constrain the 4 parameters to be physically given, then life becomes simpler. And I can tell you that for large particle sizes, your density profile is smaller in magnitude but deeper. And for small particle sizes, your density profile is narrower but bigger in size. Okay, so that happens for smaller particles droplet size. That happens for larger droplet size. And both these profiles are unstable linearly, but the nonlinear evolution is very different. And that's going to be the rest of my. I'm going to show you many instances of that particular thing. That the nonlinear evolution is very different, given the density profile is either shallow and either sharp or smaller in magnitude but deeper. Okay, so this is the, since I told you I'm already working with physically given parameters and some size of water droplets. So A equal to 10 is 10 microns. Assume that whatever liquid exists in your cloudy layer, it's made up of 10 micron droplets. Okay, so clearly, I mean, they're both unstable at a whole range of wave numbers, but the growth rate for the smaller droplets is much higher, and it peaks at a much larger wave number, which means the structures that form will be smaller. Okay? The growth rate for the larger droplet size is smaller, but also it peaks at a much smaller wave number. The structures will be larger. Okay? And we have some idea of the eigenfunctions as well. Okay, so again, this is the message. The velocity goes as A naught squared, RL goes as A naught cubed, and the settling velocity matters more to what kind of instability forms than the absolute amount of liquid water that you have in your system. Okay, so these are the simulations. These are 2D numerical simulations. The horizontal direction is periodic, the vertical direction is done using a compact finite difference scheme. So that's the initial condition: vapor, liquid, temperature, and this is vorticity. Initially, there's no vorticity. There's a small amount of liquid, and it's formed up of small sized water droplets. Okay? So you see the structures that form. If you remember Eckart's talk, you'll notice that it's the leaky kind of instability where those leaky things that form, they move around in the horizontal direction. Okay, another snapshot of the same thing. Okay, so now we'll try a large amount of liquid water, but it's still made up of very small droplets, which means there are many, many more of them. You notice that the size of the structures hasn't changed much, but the intensity of the turbulence has. The intensity of the turbulence has changed a lot simply because a lot more water was available to evaporate and create a much sharper density temperature difference, and therefore a density difference. And the buoyancy effects sort of took over, and you see a much more vigorous convection under the cloud than before. Okay. Also notice Eckart was pointing this out for his case 2 days ago. That's a measure, that blue region there, that's a measure of how much the particles would have settled on their own. This is a measure of how much the turbulence has gone because of this evaporation business. Okay. again, a still picture of the same thing. So now I show you what happens if the droplets are large. They're large droplets, but very few of them, so that the net total amount of liquid is very small. So it might look to you that like nothing's happening at the top, but you can see that the thing is still settling. If I let it go a little longer, maybe it will form some structures, but without enough water to evaporate, nothing happens. The layer just quietly subsides and dies. So slightly larger amount of liquid water, but the 50 micron droplets, so that they have a reasonable settling velocity. So now you see these structures forming, these lobes forming under the, yeah. Yes, so I mean, it's a periodic box. So it's, yes, so okay, you did see asymmetry here, lots of it. So look at that. That's not symmetric, is it? So yeah, I mean, it's a consequence of the thing being periodic and me perturbing it at a certain wave number. That wave number will probably come in at some point. Did I show you this? Yeah. So this you see these lobes. They should remind you of the Mammatus thing. An even clearer illustration happens if you let there be a little more liquid water in the top half. Okay, so that to me is it's a neat sort of Mammatus-like thing. All right. So again I reiterate my message. I'm well under time. So the settling velocity determines the stability much more, determines the nature of the structures that form much more than the total amount of liquid water. And the settling velocity is given by the droplet size. So if you have large enough droplets, you'll form these lobe-like structures, beautiful lobe-like structures. If you drop the liquid in your cloudy layer is made up of very small droplets, the structures you form will be thin and wispy. I'll tell you some more things that can be done. The first thing, of course, is the shear-driven thing the mixing-driven thing that I was telling you about. Especially since we're doing two-dimensional simulations, it's very easy to add shear. You just add a vorticity layer in the middle, in addition to everything else. Maybe adding the shear will give us, instead of Mammatus, it will give us Asperitas. We're trying 3D simulations, but haven't gotten too far with it. And I don't know what experimentalists will say that I put this compare predictions with observation at the end, but that's also something we should do. Everything you predict has to ultimately add up with what you see in the atmosphere. Okay, so I leave you with what we think is a minimal model for a Mammatus cloud. And if you have any questions, I'll be happy to. Thank
you. So in relay Bernard, the viscosity diffusion acts as a stabilizing force.
Yes.
Here, what are the stabilizing forces?
There isn't one. It's an inherently unstable thing. So it's a gravity flow, right? So it's as soon as some dense thing on top of a light thing forms, it's inherently unstable.
Yeah. In the simulations, did you give the initial perturbation as the peak of that linear stability, or you just gave a random small perturbation?
No, I gave one wave in the box, in the horizontal box.
Okay. And is that the peak or it's not?
It's not.
Okay.
I tell you why also. The stability was done in the last 2 days. We've been doing numerical simulations for years now.
Because it will be interesting to see if that peak emerges from, yeah.
True, yeah, that's something.
Because then that will tell you how the lengths are getting set.
Yeah.
You had said that in observations, the time scale for these clouds is about 10 minutes.
Yeah.
Is it determined by the amount of water that is available, or what's the physics constraining that?
So let me answer that this way. If you start with a given amount of liquid water, a layer of a certain thickness, the time for all of it to evaporate goes like the initial thickness divided by Vp. So delta Y by Vp. I think that sets the scale.
Thanks.
Do you see these mammatus structures below the anvil of the cumulonimbus alone, or also stratocumulus clouds maybe?
Yes.
Where
Good question. So the same thing kind of happens on the top, under the topmost layer of a stratocumulus cloud. And Chai and Breidenthal's paper was about that. There, the dry air is lighter and the cloudy air is heavier. But as soon as you start mixing them, the mixing causes density overhang, and that sort of, you can get plumes into the stratocumulus cloud from above, of plumes of dry air from above entering the stratocumulus cloud. So yeah, so that happens as well.
so the convection within the cloud, which is perhaps going to be more vigorous in a cumulonimbus.
Sorry, finish your question.
Yeah, so does that play a role, or is it really the
No, because this is not convection. These things are not part of the cumulonimbus. They're part of the cumulonimbus, goes up, settles at some height, spreads out. These things form here, so they're not part of the cumulonimbus.
So the convection is weak at these regions.
Yeah, I would think so. Yeah, so there may be small, there may be convection inside, but it's not nowhere near the same magnitude as a cumulonimbus. It's not that vigorous.
Right.
Yeah.
You said that the linear instability is not appropriate for your cases.
With thermodynamics.
So how do you actually find out the linear instability scales and compare it with your base flow scales? I mean, time scales.
Can you? I'm not sure I understand your question. So
I mean, you said because your time scales are comparable, that's why you could not do your linear instability.
So
how do you estimate those time scales?
There's water falling out of the cloud and evaporating. That happens on the time scale of tau s. Tau s, you remember, is the phase change time scale. We simply could not get the linear instability to work, and this is our guess for why it's not working. It's not working because the base state is itself changing at a very fast rate. We have tried everything we know and we can't get it to work. Do you have a better guess, maybe, or why it's not?
Time scales from your simulations were looking pretty explosive, so to speak. So I was wondering.
Correct. So if the instability happens rather fast,
so
the tau s is also very small. Those two don't.
The base state, changing of your base state was slower than your instability time scale. That's what in your simulation.
There doesn't seem to be enough of a difference between them.
I have a very general question. So these Mammatus clouds, are there any specific latitudes over which they form, or they can form anywhere?
They form everywhere. There isn't, as far as I know, in that paper, for example, they've been seen in the tropics. They've been seen in temperate zones.
Thank you.
Well ahead of time.
If there are no questions, maybe let's thank the speaker.